why don't we try implementing the cat program and seeing how we can read from and write to standard input and output using fundamental basic system calls. And to do this, we're going to import some functions from the Unix standard, or these are POSIX standard functions. And we're going to later try adding some file related controls for being able to open a file rather than read from standard input streams. So to begin with, we need a buffer, right? So at the fundamental system level, we're always reading to and writing from buffers. So let's go ahead and just set up a static buffer here, and we'll set up a defined constant that will be buffer size, that is, say, 80. And let's go ahead and make a character array that is buffer named buffer of buffer size. Okay. And so we've got our global, which is in static memory, buffer set up. And what we're going to do is read this buffer into, read from standard input into this buffer. So how do we do that? Well, there's a system call that's called read. And next we need to give it, where are we reading from? These are those file descriptors we were talking about before. And remember, 0 is standard input, right? Now, rather than using 0 here, but actually I'm going to use 0 and 1 for now, and then we'll come back and we'll replace this with names that will avoid these magic constants. So even though these are well-known established numbers for the past 50 years, it's good to use names here just so we don't accidentally confuse what we're thinking about. 0 has many meanings, and in this case it means standard input, right? So we're reading from standard input, and where are we reading to? We're reading into a buffer. And what are we reading? Well, the next thing that we're saying is read up to 80 bytes, right? Once you have 80 bytes, that's as much as my buffer can hold, and I'll have to call read again to get more than that, okay? So now we've got this buffer should be filled from standard input, right? And why don't we just go ahead and try writing from this buffer back out, right? So we can write back out, and what did we say was the file descriptor for standard output? Well, that's file descriptor number 1. We're writing from buffer. And how many bytes are we writing? Well, if we write 80 bytes, that would make sense if we had 80 bytes of input, but we don't actually know if we filled the buffer, right? If we entered a line that had only 5 characters in it, we would really only want to write back out 5 characters. So it turns out this idea that we need to know how many characters of input we had is a common one, right? And read returns to us how many bytes it was able to fill into our buffer, right? So read actually gives us back the number of bytes that it was able to fill. So I'm going to set up a variable, and its type is s size t, which is a small size. The number of bytes we're reading here and talking about is never going to be the size of our entire memory subsystem, like you can imagine with a size t, which was on a 64-bit system, an 8-byte piece of data. Here, what we're talking about is a smaller size because our buffers can never be quite that big. And the smaller size, I think it's always going to be either 16-bit or 32-bit. It doesn't actually matter because it's going to be system dependent. As long as we use this type, it will be correct and we'll be just fine. And so our smaller size variable name is going to be bytes read, right? So we'll keep bytes read available, and we're going to assign to bytes read the result of reading into our buffer, right? And so rather than writing 80 bytes out, no matter what, we're going to write out the number of bytes that we read in. Okay, so this program will read up to 80 bytes from standard input, and it will read as soon as we have a new line available to us to read. When we press enter on our terminal, that line is sent from our terminal to the operating system saying, hey, here's some more input. And then the read command from the process that's trying to read from that terminal can access that data and pull it in. Right? And then we're going to write that back out. So I'm going to switch over to my terminal, and I'm just going to use the basic GCC here to compile this program and then just run a.out. So we're waiting on standard input, and if I write hello world, we have hello world printed back out, and our program is terminated, right? And so this is as fundamental, just about as fundamental, without getting into assembly and machine language code, of a implementation of reading one line of input in and writing it back out, right? So what can we do to make this a little bit more like cat? Well, we can read in a loop, right? So we can say while bytes read, and that number will be greater than 0 as long as there's more input coming in, right? While bytes read is assigned the result of reading up to 80 bytes. And we've got a syntactical rule here that's telling us we should improve our, when we use an assignment statement inside of a while loop, we should surround it in parentheses, just in case we were to add additional conditions after this. But in this case, we're just surrounding that in parentheses. We're saying while bytes read is assigned read from standard input, and we'll still go correct that. We need to make that actually a named constant. Read up to 80 bytes. And in 80 bytes, we already actually have a named constant for, which is our buffer size. So I'll go ahead and fix that little code smell there. And let's try this again. I'm going to run gcc cat.c and a.out again. And we're waiting for a line, hello world. And now we're waiting for another line. This is cat. Right? And if I press Control D, that sends the end of stream character, which means no bytes are read, and that causes our loop to terminate. So we've got a very simple implementation of cat here without any support for arguments, right? So we'll come back to that. Let's try fixing up our code here. This 0 and 1, remember, those are the entries in the file descriptor table for the given process, right? That we're running, which would be cat in this case. And now what we want to do is make those named constants, right? So it turns out there are some named constants already set up for us. Standard in file no, and standard out file no, right? So the file number is the file descriptor number, and those are defined in the Unix standard header file. So we can convince ourselves that this still works by running GCC, and we're compiling cat.c, a.out, hello world, test, and it seems like this is still working, right? So these are named constants, but what I want you to know is those constants are just integer values that are related to that file descriptor table we talked about, right? And so if we wanted to, we could use redirection now. This is our simple program, right? This is our simple implementation of cat.c. And if we wanted to convince ourselves that redirection actually works like it was explained, we can prove that to ourselves right now, right? So how can we do that? Well, the first thing we could do is if we look in the directory this cat.c file is in, if I were to say cat file demo and then input.txt, this is that input file we were using in the previous demo. And what if I redirect that as input to my a.out program? So a.out, and I'm going to use the less than symbol for input redirection. So notice I'm saying redirect this to be the standard input of a.out, right? So when I press enter, notice those contents are printed out to the screen. We didn't change anything at all about the implementation of this program, right? We're reading from standard input. This program is exactly the same as we had it before, but because of the way we went to run this program, we redirected standard input to not be reading from the terminal. We made that connection to a file instead, and it was the bash shell that made that different connection, right? Similarly, and just to convince ourselves, I'm not going to recompile or anything, /a.out, hello world, right? We're printing back to standard output. If I end that input with Control D, and we now redirect our output /a.out to say output.txt, and I write some lines, notice I'm not seeing that output back at my terminal because we're redirecting the output of this standard output file descriptor to be sent to the output.txt file instead of our terminal. This is output from a.out and Control D to end my input. And now if I list my files here, we have this output.txt. And if I were to open it in Vim, there's our output, right? And notice that was us running this program that we had just compiled. We just wrote it from scratch, all we're doing here is redirecting our output from the shell level, right? But the program itself is just reading from standard input and writing to standard output. So what if we wanted this program to be able to read from a file instead of standard input? How could we make this read use a different identifier here? Well, let's set up a variable named file descriptor, or FD for short. And this is a terse and highly contextual use of a variable name, but it's so common. I'm going to break the norm of using fully written out, full word variable names and use a conventional name here. FD is always going to be short for file descriptor, and it's going to be assigned standard in file number. That's just an idiom that you'll see in the Unix world, right? So we are going to, rather than read directly from standard in, let's read from this file descriptor, okay? Now, just to convince ourselves that this still works out, if I were to compile again and run this program again, right, everything's fine, right? The fact that we pulled this out into a variable is no problem. But what we want to do now is say, rather than using a file descriptor of standard in, I'm going to try reassigning this to be the result of opening a file, right? And we're going to open a file, and let's just open the file demo and input.txt file. This is the one we were looking at before. So the first argument to this open file system control function is the path of the file that we're opening. And next is the mode or the flag that we're opening this file with. And these are things that you can look up and you can find on the internet for reference if you look into the the open function. But because this is a very low level system call function in terms of how we think about writing C programs that access the operating system. Typically you would use fopen instead, and it's going to use different semantics here. So I wouldn't worry too much about this flag, but we're saying open this in a read-only mode, right? And we're going to read from that file. And then the other thing that we need to do if we're going to be good citizens here is we need to close this file descriptor, right? And if we're opening a resource from the operating system, when we're done with it, we should close it. Technically, because this program ended immediately after this, it wouldn't have been that big of a deal. All of this gets reclaimed anyway. But because there's a chance that you would want to go extend this program and create behavior beyond this, it's always good practice to, whenever you open a file, be sure you close it as well. All right, so let's try this out. Okay, so I'm going to compile this program, gcc cat.c, and then run it. And wow, look at that. Our contents were read directly from this file descriptor rather than from standard input. And we just read the contents of that file before printing them out line by line. So what if we wanted to make this behave closer to the actual cat program? And we won't go all the way on this, but what if we wanted to make it possible to have arguments here? Well, we know that we can give an arg count parameter to our main function and an arg value that is a pointer to an array of strings, right? So this will be our arg values, right? And when we start our program, these two values will be populated with any arguments that we pass in. Remember, our argc is always going to be at least 1 because that's going to be the name of the program or the path of the program that we ran. And then anything after that will be subsequent arguments we give to our program as we start it up. Okay, and so we could say something, I'm going to be very naive here. Again, this is just for a simple demonstrative purpose. If we say if argc is greater than 1, that means if there is a path that we are trying to, oops, and I spelled argc wrong up here, argc. Okay, if there is more than just the program, if there is an actual argument that we're passing in, this is when we are going to, rather than using standard input, we're going to use a file and open up a file descriptor here, right? So if argc is greater than 1, we don't want to hard code in this path, right? We want this to come from the argument value, the first argument value, right? And so remember, argv0 is the name of the program. Argv1 would then be the first argument, right? Now, we can close the file descriptor in either case. Actually, it turns out we can close standard input at this point because we're done reading at this point in the program, and it we get closed anyway as the program wraps up. All right, so let's try this out. So now if we compile our program and a.out normally, notice that because we didn't provide an argument here, I can type into standard input, hello world. It's printed out to standard output. But if I were to run this with an argument such as file demo and then input.txt, notice that we then had an argument count of 2. So this was our first argument, second argument. And then we opened up a file descriptor and we opened a file from this path that we passed in, right? And ultimately we wrote out each line as we read it in from that file descriptor. Well, what if this file didn't exist, right? So if this file didn't exist, we could test that by asking if file descriptor is equal to -1, which is what the open function will return if there's an error opening this file. This might have also been another type of error, like we didn't have permission or other things, but we're gonna just try out an example here for demonstrative purposes of a file that doesn't exist. In this case, why don't we write to standard error file number, which we could have just written the integer number 2 here, exact same thing, right? What are we gonna write? Well, our error message will be no file, and the number of bytes that we wanna write will be 1, 2, 3, 4, 5, 6, 7, and we should probably end this with a new line, 8, so 8 bytes, right? We don't need to write the null terminating character because we're just sending data across the pipe, right? And we should probably exit here too, and we can exit with a status code of 1, or if I had imported standard lib, we would have done, actually, let's just go ahead and do it, include standard lib.h. We would exit with an exit failure code, right? Because we didn't find that file. I want to point out that in cat, it doesn't actually do this, right? We don't exit here. We print something to standard output, but we might still have other things that we would cat out to the screen. Okay, so I wrote my file, and now I'm going to compile it and a.out. So this time around, hello. All right, that's still working. But if we try a file that does not exist, notice that we have no file printed to standard output, or sorry, standard error, and then the program exits. Right? If we wanted to convince ourselves that this was actually going to standard error, we could redirect standard output to standard out.txt, and notice we still see those contents printed to the screen. All right, and so just as a final follow-up on the diagrams that we looked at before, right? We have, in this case, our terminal. And our operating system file table has a T0 entry in it for the terminal. And that's what gets us input to our screen and output to our screen, right? And we can read and write from that. And then our process here, when we run a.out, right? A.out has the 3 file descriptors in it, 0, 1, and 2 set up by default, right? And so what I want to talk about here really quickly is actually the case where we run with a file that does exist, because that's where I was a little bit hand wavy in the previous videos, but now that we've seen the code that implements this, we can talk a little bit more explicitly about it, right? So 0 is connected to T0 standard input. It's being read from the terminal. Standard output will write to the terminal, and standard error will write to the terminal as well. Okay, so what is it that happens when we actually run this program with a file input that does exist? So I'm going to switch back over and do that really quickly. Right, so I'm going to clear my output here and say /a.out, and then file demo input.txt. So that's a file that existed, and we read it out to our input, right? So what is it that, or sorry, to our output. So what is it that actually happened in order to make this work? And so we've got these standard streams available, right? But something special happens when we reach this line, right? And we reach this line because we have this file that was one of the arguments, and that caused us to reach this point in our simple cat implementation program. And this is making a system call called open, right? And open here, and the path is going to be, file demo input.txt. Right? And so what this does is it says, okay, operating system, set up a new file entry, and we're saying read only. So we're going to set this up in a read mode, and some file on our file system is going to be hooked into this entry in the OS file descriptor table. And what it's going to do in the process file descriptor table is set up a new entry here. Right? And so this is going to be our new entry. And here we're saying it's 3. Which is just this file entry that we are connected to F, right? And actually we're reading from this, so I should draw the arrow in the other way, right? And so this was a new file descriptor that we established in our program, and we're deciding to read from it based on the implementation of this cat program, right? And the implementation is saying, hey, if you give me a first parameter here, I'm going to read from a file specifically instead. And now notice what the program was doing. The program was saying, all right, the integer, which of these entries in my file descriptor table for my process I'm going to read from, by default, it's going to be standard input, which is 0, right? But if we run it in this special way, we're going to overwrite that variable with the value that comes back to us from open, which by default, the operating system isn't going to do something clever here. We're not going to pick a random number. We're just going to increment the last used file descriptor of this processes table and choose the next one that's available. And so in this case, it would be 3. And then when we go to read, notice this gave us the flexibility of either reading from standard input in our program or from some specific file that we reassigned that variable to. And notice that this program didn't really need to care whether standard input was coming from somewhere else if we ran the program in a specific way. Right? And this is a very common idiom or expectation that you have in many programs that operate on textual files. If you don't provide a file input, it will read from standard input by default. Or if you provide a dash, like we looked at in the past video, that was another way of very clearly indicating, hey, read from standard input. But it turns out, as I could have demonstrated, and we could look at really quickly, if you just run the program cat without the dash, this is also running in the same mode that we just implemented, right? So we're reading from standard input, writing to standard output. grep and other programs work in the same way, where if you provide a file, we're going to use that as where we're pulling our input from, or you could redirect input to it. And so there's these various ways we can connect programs together, and often conventions that allow us to run a given program with specific arguments. So in this video, we implemented a very simple cat program. We didn't have support for multiple arguments, but you can imagine that's just a loop that loops through each of your arguments one by one and does the same process for them. But hopefully this conveys that there's really not a lot of, well, there's a lot of magic underneath the hood at the operating system level, but the API we're exposed to for these system calls is pretty basic and straightforward. We're just reading bytes from a buffer or writing bytes to a buffer in the operating system.